Hey everybody, we're going to be doing a new topic in calculus today, antiderivatives. So we're going to stop working with derivatives for just a little bit, and we're going to work with something called antiderivatives. And here's how we define antiderivative. And before I start this conversation, let me say that I am definitely making a distinction between capital F and little f. I'm not going back and forth between capital F and little f whimsically and indiscriminately. I am making a deliberate distinction between capital F of x and little f of x. So I want to make that clear. Capital F of x represents one thing, and little f of x is going to represent something else. So now on with our definition of antiderivative. The function capital F of x is an antiderivative of the function little f of x exactly when capital F prime of x equals little f of x. So in other words, the antiderivative, capital F of x, is the function that we compute the derivative of to get little f of x. The antiderivative is the function that we compute the derivative of to get little f of x. Now let's look at an example. Let's take little f of x equal 3x squared. This is little f of x. So what should the antiderivative of little f of x be? Would we say maybe x cubed? If we do, that ought to make sense, because the derivative of x cubed is 3x squared. So capital F of x equals x cubed should be the antiderivative of 3x squared. But let me ask you something. Can I do this? What about that? Could I say that capital X cubed, could I say that x cubed plus 1? Could I say that capital F of x equals x cubed plus 1 is the antiderivative of 3x squared? Well, that all depends. If I take the derivative, or if I compute the derivative of this function, do I get 3x squared? And the answer is, yes, I do. So x cubed plus 1 is an antiderivative of 3x squared, just like x cubed is an antiderivative of x squared. And could I do this? Could I say that x cubed minus a half is an antiderivative of 3x squared? That all depends. If I compute the derivative of x cubed minus a half, do I get 3x squared? And the answer is yes, I do. So x cubed minus 1/2 is an antiderivative of 3x squared. Dot, dot, dot. So here's what we've noted. The antiderivative of a function f of x is not unique. In fact, there are infinitely many antiderivatives of a function f of x. When we were given the function little f of x equals 3x squared, all we had to do was take one antiderivative, x cubed, and just add different constants to it. And every time we add a different constant to x cubed, we'd get a different antiderivative of 3x squared. So we might wonder, in our example, we had little f of x equals 3x squared, and antiderivative f of x equals x cubed plus some constant. And we might wonder, is it possible to have two antiderivatives of 3x squared? And let me just write down some examples here. x cubed plus 1, x cubed minus a half. All of the antiderivatives of 3x squared that we looked at were x cubed plus a constant, x cubed plus a different constant. And we look at these antiderivatives and say, well, the non-constant part of the antiderivative is the same, only the constants differ, and we might wonder if that has to be the case. And we answer that question right here. If capital F of x is an antiderivative of little f of x, then all other antiderivatives of little f of x are of the form capital F of x plus c. So if capital F of x is an antiderivative of little f of x, and a function doesn't look like this, then it's not an antiderivative of little f of x. Another way of saying this is that all antiderivatives of little f of x differ from one another by a constant. So take any two antiderivatives of this function, and the only difference between them is going to be the constant term. Let's work on some notation. If capital F of x is an antiderivative of little f of x, then we can write the following. This expression. Now, I'm diagramming all of the main characters here. Capital F of x is any antiderivative of little f of x. This thing, the elongated s, is called an integral sign. F of x, little f of x, the function whose antiderivative we're trying to compute, is the integrand. Dx is the differential of x. And this constant, this plus c, is called the arbitrary constant of integration. And even though I've labeled the terms of this expression, I think we should make a comment on what these things are and how they function. Okay, we'll identify some of the main characters here. The integrand, in this case, little f of x. The integrand is the function whose antiderivative we wish to compute. So this thing, this function, is the integrand. Next, the integral sign and the differential of x. These two things, the integral sign and the differential of x, work together as a single instruction telling us to compute the antiderivative of the function in between. So this integral sign, this differential, tell us the following. They say, hey, look at what's in between and compute the antiderivative of that thing. So the integral sign and the differential work together as a team, as a single instruction that tell us compute the antiderivative of what's in between. And I will say this. They work together as a team. You will never see an integral sign without a differential. These two go hand in hand pretty much. And an integral sign without a differential is meaningless. It's just as meaningless as sine. Sine? Really? Sine of what? Sine of x? Sine of an angle? Without an argument here, without this, the sine function is meaningless. This means something, this doesn't. And similarly, this means something, that doesn't. The integral sign without the differential means absolutely nothing. So the integral sign and the differential work together as a team, as a single instruction, and they say to us, hey, look at what's in between and compute the antiderivative of that expression. Now, there's one more thing that I haven't identified or commented on, and I'll do that right now. The arbitrary constant of integration. The arbitrary constant of integration reminds us that there are infinitely many antiderivatives of the function little f of x, all of them differing from one another and from capital F of x by a constant. So this one function, little f of x, has infinitely many antiderivatives, but they all differ from this function, capital F of x, and from one another by a constant. So every antiderivative of little f of x has to have this form, capital F of x plus some constant. Now, let me give a few more remarks about notation and how we interpret it. Okay, given the expression integral sine f of x dx, and we can refer to this as the antiderivative of f of x or the integral of f of x. But given this expression, integral sine f of x dx, we interpret the integral sign and the dx, the integral sign and the differential, as an instruction that tells us to compute the antiderivative of the expression in between, little f of x. So given this expression, we consider the integral sign and the differential to be an instruction that tells us to compute the antiderivative of little f of x, the expression in between. And let's give an example. Here's an example. Given the expression integral sine 3x squared dx, we interpret the integral sign and the differential as an instruction telling us to compute the antiderivative of 3x squared, the expression in between. So given this expression, the integral sign and the differential dx act as an instruction telling us to compute the antiderivative of 3x squared, the expression that's in between. Now, there's also another way that we can look at this entire expression. There's another way of looking at this thing. We regard the entire expression, this whole thing, as being the antiderivative of little f of x. So this whole thing, as far as we're concerned, this is the antiderivative of little f of x. So in other words, this thing is the same as capital F of x plus c. This is the same as antiderivative of f of x plus c. Now let's look at another example. We regard the entire expression, integral sine f of x dx, to be the antiderivative of little f of x. So integral sine little f of x dx is the same as capital F of x plus c. We see these two things as being exactly the same. Now, let me erase part of that. Looking down at the bottom of the screen, we regard the entire expression, integral sine of 3x squared dx, to be the antiderivative of 3x squared. So this entire expression, as far as we're concerned, it's the antiderivative of 3x squared. So this entire expression in our mind is the same as x cubed plus c. Remember, x cubed was one of the antiderivatives of 3x squared. So this entire expression we view as the antiderivative of 3x squared, namely x cubed plus c. And I'm stressing that because we're about to consider some rules for antiderivatives. Remember when we did derivatives and we had to use the limit process and we had limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, and we had to compute the derivative that way. Even for a simple function like x squared, it wasn't easy. And my goodness, for a function like sine of x or secant of x, computing that derivative using the limiting process, that would be a major challenge. So we came up with rules and properties of derivatives that help us to compute the derivatives of just about any function that we'll encounter by inspection or with just a little bit of computation. And we want to do the same thing for antiderivatives. So we're going to use this notation to list some properties and rules of antidifferentiation or computing antiderivatives. But first, I'm going to throw a new term into the mix. I think this will be the last of our new terminology for a while. Antiderivatives are sometimes called integrals. The reason for that may become apparent in Cal 2. Antiderivatives are sometimes called integrals. And the process of computing an antiderivative or an integral is called antidifferentiation or integration. So when we compute an integral, we're doing integration. When we compute an antiderivative, we're performing the process of antidifferentiation. Now, on with our properties. Oh, I forgot something. Before we do the properties of antiderivatives, I do want to point out, and this is very important, it's important that we have this concept. Antidifferentiation is the reverse process of differentiation, and vice versa. Differentiation is the reverse process of antidifferentiation. Each one essentially undoes the other. We start out with a function capital F of x, and we differentiate, and we get capital F prime of x, which is little f of x, since capital F of x is the antiderivative of little f of x. And now what happens if we antidifferentiate or integrate? Well, the antiderivative of little f of x is capital F of x plus some constant. So if we differentiate and then antidifferentiate or integrate, we get back what we started with, up to maybe a constant term. Now suppose we do these operations in the other order. Let's take a look. Yeah, let's suppose we do this in the reverse order. We start with the function little f of x, and we antidifferentiate or we integrate. If we integrate, we get capital F of x plus some constant c. And then suppose we follow that up by differentiation, computing the derivative. C is a constant, so the derivative of c will be 0. And since capital F of x is an antiderivative of little f of x, when we differentiate capital F of x, we get capital F prime of x, which is equal to little f of x, because capital F is an antiderivative of little f of x. So the point here is that if we antidifferentiate or integrate and follow it up with differentiation, we get back exactly what we started with. So these are essentially the reverse processes of one another. And I want to beat this drum a little bit more. I want to look at it from another perspective before we do the properties of integrals. Here's another perspective from which we can view derivatives and antiderivatives. When we differentiate or compute the derivative of a function, we're given a function, capital X, and asked to find its derivative, capital F prime of x, or little f of x. So when we differentiate, we're given a function and asked to find its derivative. When we antidifferentiate or integrate, we're given the derivative of a function, capital F prime equals little f of x, and we're asked to find the original function, capital F of x. Yeah, when we differentiate, we're given a function, and we're asked to find its derivative. When we antidifferentiate or integrate, we're given the derivative of a function, capital F prime or little f of x, and we're asked to find the original function, capital F of x, plus some constant. So keep these things in mind. The concepts are fairly important. Here are 4 basic properties of antiderivatives or integrals, closely related to analogous properties of derivatives. And the relationship exists because differentiation and antidifferentiation are just reverse processes of one another. They're very closely related, so they should have similar properties. And with derivatives, think about this. When we compute the derivative of a constant times x, what do we get? Let's say the derivative of 3x. Well, the derivative of 3x would just be 3. And that's right. So suppose we computed the derivative of a constant k times x. That derivative would be k, wouldn't it? So what would the antiderivative of the constant k be? It would be the function that we had to compute the derivative of to get k, kx, plus the arbitrary constant of integration. So the antiderivative of a constant is a constant times x that constant times x, plus the arbitrary constant of integration. And we have a power rule for derivatives. It's not surprising that we have a power rule for antiderivatives. And here it is. Now, interestingly enough, with the power rule for derivatives, it works for any exponent n. With antiderivatives, the power rule works for any exponent n except n equal -1. And we see what goes wrong when n equals -1. We plug it into this formula, we get x to the 0, which is 1, over 0, which is undefined. Ooh. No, this formula won't work if the exponent of x is -1. But it works for all other exponents. And just like we have a property about the derivative of a constant times a function for derivatives we have the derivative of a constant times a function equals the constant times the derivative. And here we have the antiderivative of a constant times a function equals the constant times the antiderivative. And it tells us that if we're computing the antiderivative of a constant times a function, we can go ahead and write the constant down and then just go about the business of computing the antiderivative of the function. And when we're done, we can multiply the two together. It also tells us something else, something visually. When we compute the integral or antiderivative of a constant times a function, visually what we're doing is we're moving this constant factor from one side of the integral sign to the other side of the integral sign. With a constant factor in the integrand, we can do that, but only if this is a constant factor. And we will look more closely at this property in a little bit. With derivatives, we had the property that the derivative of a sum or difference is the sum or difference of the derivatives. And what that meant for us is that we can compute the derivative of a sum or difference one term at a time. The same thing holds true for antiderivatives. The antiderivative of a sum or difference is the antiderivative of the first plus or minus the antiderivative of the second. So what that means for antiderivatives is that if we're computing the antiderivative of a sum or difference, we can compute that antiderivative one term at a time, term by term, and then we just add the results together. Now there's room for a few more properties that I'm not going to list, but if you'd like, you can number the list from 5 all the way up to 10. I have 6 more properties that we should see before this lecture is over. So if you want, you can number from 5 down to 10 and leave those spaces blank temporarily. We'll come back to number 5 and number 6, etc. in just a little bit. Now, maybe I can justify this form of the power rule. To understand the power rule for antiderivatives, keep in mind that antidifferentiation is the reverse process of differentiation. Now think about how we apply the power rule in differentiation. Mechanically, it's a 2-step process. The first step is we multiply by the exponent. So we get n x to the n. And then the second step is we subtract 1 from the exponent. 2 steps. multiply by the exponent, subtract 1 from the exponent. Now, since antidifferentiation is the reverse process of differentiation, we have to undo each of these steps, and we have to undo them in reverse order. Think about it. If I give you directions on how to get someplace, and I say, take your first left, take your first left after that, take your first left after that, and then take your first right. How are you going to get back? Think about this. I say, take your first left, take your first left again, take your first left again, and then take your right. How are we going to get back? We have to undo these steps, but in reverse order. So we'll take our first left, and then we'll take a right, we'll take another right, we'll take another right. The same kind of logic applies to the power rule and antidifferentiation. So suppose that we start with the function x to the n. The first thing we want to do is undo this step. So how do we undo the step of subtracting 1 from the exponent? That's pretty easy. Add 1 to the exponent. And that's going to give us x to the n plus 1. The next step that we have to undo is multiplying by the exponent. And how do we undo that? We divide by the new exponent. And so that's exactly how we get our power rule for antiderivatives or integrals. Now, just as we did for differentiation, we're going to do a bunch of examples for integrals or antiderivatives. The antiderivative of the constant 3. According to property 1, we're going to multiply it by x and add a constant of integration. So 3x plus c. I guess the question now is, did we do it correctly? If we did, then this should be the function that we compute the derivative of to get the original expression. What do we get when we compute the derivative of this? C is a constant, so its derivative is 0. And the derivative of 3x is just 3. Yep, we did it right. Let's look at a few more. Again, the antiderivative or integral of a constant, property 1 says that we take that constant and multiply it by x and add c. The integral of -3, multiply that constant by x and add a constant of integration, and there we go. Now, how about this? What about that? The antiderivative of pi. Pi is a constant, right? So we should get pi x plus c. Let's do some power rule exercises. the integral or antiderivative of x cubed. The power rule says we do two things. First, we add 1 to the exponent. And then we divide by the new exponent. Okay, let's try another one. The power rule says add 1 to the exponent, then divide by the new exponent. So we add 1 to the exponent, and then we divide by the new exponent. And that's x to the 10th over 10 plus c. And if we want, we can write it as 1/10 x to the 10th plus c. Okay, x to a power, add 1 to the exponent, divide by the new exponent. So we add 1 to the exponent, we get x to the negative 2. We divide by the new exponent. Whoops, I forgot my plus c here, didn't I? Okay, square root of x. We have to use that word that I love so much. Rewrite this using exponents. So we have x to the 1/2. And the power rule says add 1 to the exponent. So that's x to the 3/2. Divide by the new exponent. And let's see, if we divide by 3/2, that's the same as multiplying by the reciprocal, right? 2/3 x 3/2 plus c. Okay, looking good there. Antiderivative of x to the 15th. The power rule says add 1 to the exponent, divide by the new exponent, and there we go. Antiderivative of cube root of x. We rewrite. And we have antiderivative of x to the 1/3 dx. We add 1 to the exponent, so let's see. 1/3 plus 3/3 is 4/3. We divide by the new exponent. And that turns out to be 3/4 x to the 4/3 plus c. So I think we got properties 1 and 2 down just fine. I guess we'll throw property number 3 into the mix now. we have the antiderivative or the integral of a constant times a function. So property number 3 applies. And it says we can move the constant factor out in front of the integral sign. So I guess we'll do that. And we compute the antiderivative of x to the 15th. We add 1 to the exponent, divide by the new exponent. And let's see, 4 over 16, x to the 16th plus c. Now, maybe we can take something away from this. It's a good observation to make that if we have a constant factor of the integrand, we can move that constant factor out in front of the integral sign. We can also look at this and say, if we have the integral or antiderivative of a constant times a function, we can write the constant down and then worry about computing the antiderivative of the function. And I guess we want to look at this both ways. Let's try something like this again, doing it the second way. We have the integral or antiderivative of a constant times a function. So we can write the constant down and then just worry about computing the antiderivative of the function. It's a power rule problem. Add 1 to the exponent and divide by the new exponent. And we can do a little bit of canceling here, but not much. And I think typically this is how we're going to integrate or antidifferentiate a constant times x to a power. When we do the same thing with derivatives, typically we can do it in one step. If we have the derivative, let's say, of 3x to the 4th, we can write the constant down and then compute the derivative of x to the 4th and multiply the constants. But we learned very quickly when we were doing this sort of thing with derivatives that we could turn this into essentially a one-step process. Bring the exponent down and multiply it by the constant, subtract 1 from, let me write the expression down first. We learned that with derivatives we can pretty much do this in one fell swoop. Bring the exponent down and multiply it by the constant, and then subtract 1 from the exponent, and we're done. Typically, we're never going to take the analogous process for integrals and antiderivatives and turn this into a one-step process. Typically, when we integrate a constant times a function to a power, we're going to have to take 2 steps to do it. And perhaps it's because our brains are all hardwired the same way, and we don't really feel as comfortable dividing as we do multiplying. So when we do the integral of a constant times something raised to a power, typically we're always going to do it in 2 steps. And in calculus, everybody that does calculus does these things the same way. I guess because to an extent our brains are all hardwired the same way. So integrating a constant times a function, typically we write the constant down, we integrate the function, and then we multiply it together. We just never really seem to be able to combine this into one step with any ease. Now let's do some more. Those were good examples. Let's do some more good examples. Let's see, will these cancel out somehow or not? I don't know. Let's write down the constant out front, 5/3. And now we're going to add 1 to the exponent. So 4/4 plus 3/4 is 7/4. And then we divide by the new exponent, 7/4. No canceling going on here at all. So 5/3 times 4/7, x to the 7/4 plus c. And that's going to be 20/21 x to the 7/4 plus c. Let's do another one. Two-fifths x to the 2/3 dx. We'll write the constant down, and then we'll add 1 to the exponent. 3/3 plus 2/3 is 5/3. And we'll divide by the new exponent. And let's see, that's 2/5 times the reciprocal of this, 3/5 x to the 5/3 plus c. I'm getting weary of this. Let's do something with whole number exponents again. Antiderivative of a constant times a function. So we'll write down the constant, and then we'll do the power rule. Add 1 to the exponent and divide by the new exponent. And 12 divided by 6 is 2. Voila. Now we're making good progress. Time to move on to step number 4, or property number 4. I very foolishly erased property number 4 right before we needed it. But what property number 4 really told us was that the antiderivative, or the integral, of the sum or difference of functions can be computed one term at a time. Just compute them term by term. So we start with the antiderivative of the first term. We write the constant down, and then we take x, we add 1 to the exponent, and divide by the new exponent. Then we move on to the next term, minus 2x. We add 1 to the exponent. X is x to the first power, isn't it? So we add 1 to the exponent, and we get x squared over 2. And here we have the antiderivative of a constant. That's just the constant times x. And that constant of integration. And some of these constants actually do cancel. The sum or difference of 5 terms. We'll take the first one, write down the constant, and then add 1 to the exponent, so we have x to the 6th, and then we divide by the new exponent. Then we move to the next term, negative 4x. We add 1 to the exponent and divide by the new exponent. Move to the next term, write the constant down. X, add 1 to the exponent, x cubed, divide by the new exponent. Move to the next term, negative 9x. Add 1 to the exponent. Well, this is x to the first, really, isn't it? So we add 1 to the exponent and get x squared, and divide by that new exponent. 5 is a constant. The antiderivative of a constant is that constant times x. And then we add the constant of integration. And can I simplify this? I think so. X to the 6th. These guys cancel. These guys cancel. These guys cancel somewhat. Oops, those don't cancel. Okay. So we get x to the 6th minus x to the 4th plus x cubed. No, we don't. 2x cubed. Foolish me. Minus 9 halves x squared plus 5x plus c. So when it comes to computing the antiderivative of a polynomial, not a big deal. Not a big deal at all. Now remember we had that list of properties and we only did the first 4 properties on the list, but there were really 10? Well, now we're going to do 5 through 10. On your mark, get set, go. I'm going to do property 6 first, and we ask ourselves, what function do we have to compute the derivative of to get cosine of x? And we say sine of x. Sine of x is the function that we compute the derivative of to get cosine of x. So that means the antiderivative of cosine of x is sine of x plus some constant. Now, I'll ask this. I'll say, what do we get when we compute the derivative of cosine of x? Well, when we compute the derivative of cosine of x, we get negative sine of x. And then I'll say, okay, so then what function do you think we should compute the derivative of to get positive sine of x? And the answer would be negative cosine of x. The derivative of negative cosine of x equals positive sine of x. So negative cosine of x is the antiderivative of sine of x. Now, let's try this one. What's the derivative of tangent of x? And the answer is secant squared x. So tangent of x is the function that we have to compute the derivative of to get secant squared x. So what should the derivative of secant squared x be? And the answer is tangent of x plus some constant. Now, we'll try looking at the cosecant of x, or cosecant squared of x. And I'll ask this, what do I get when I compute the derivative of cotangent x? Well, the derivative of cotangent x is negative cosecant squared x. So if I compute the derivative of cotangent x, I get negative cosecant squared x. What would I have to compute the derivative of to get positive cosecant squared x? Negative cotangent x? That's right. The derivative of negative cotangent of x is positive cosecant squared x. So negative cotangent x is the antiderivative of cosecant x squared, or cosecant squared x. Now we move down here. And I ask you, what do we get when we compute the derivative of secant of x? And you say, well, the derivative of secant of x is secant x times tangent x. So then what's the antiderivative of secant x times tangent x? Secant x plus c. And let me ask you something else. What do we get when we compute the derivative of cosecant x? Well, the derivative of cosecant x is negative cosecant x cotangent x. So what about positive cosecant x cotangent x? That antiderivative. If the derivative of cosecant x is negative cosecant x cotangent x, what would we have to compute the derivative of to get positive cosecant x cotangent x? Wouldn't it be negative cosecant x? So that means that negative cosecant x is the antiderivative of positive cosecant x cotangent x. If you're doing Cal 2, you're going to have to know these. For the final exam, make sure you know antiderivatives of sine and cosine for sure. And let's do an example or two. Antiderivative of 3 sine x plus 6 cosine of x. It's the antiderivative of the sum or difference of functions. So we do the antiderivative term by term, one term at a time. So we do the antiderivative of this term, and it's a constant times a function. We write down the constant, and then we compute the antiderivative of sine of x, which is negative cosine of x, plus c. And then we go to the next term. It's the antiderivative of a constant times a function. So we have 6 times the antiderivative of cosine of x, which is sine of x plus some other constant. So I'll call it C2, and I'll call this constant C1. And I'll simplify it a little bit. I get negative 3 cosine of x plus 6 sine of x plus 3c1 plus 6c2. So I have a constant times a constant here. What's a constant times a constant? It's another constant, right? So this is a constant, this is a constant. What do we get when we add a constant to a constant? Another constant, right? So this is all one big constant, 1 plus c. And there's a point to be learned here. When we're computing the antiderivative of the sum or difference of terms, compute the antiderivative of each term and then just add one constant of integration to the end. Yeah, compute the antiderivative of each term minus the constant, and then just add one constant at the end. So I didn't need to add a plus C1 and a plus C2 here. All I needed to do was add one constant right here at the very end. All I needed to do was go like this. 3 times negative cosine of x plus 6 times sine of x, and then just add the plus c at the end. So compute the antiderivative of the first term, compute the antiderivative of the second term, and then just add one constant at the end. That's all that I had to do. But of course, if I'm new to this process, I wouldn't know that unless I experimented around, which is what we just did. But when we compute the antiderivative of a sum or difference, just antidifferentiate each term and then add our constant at the end.